Hello again. In this example, I just want to show off the fact that if you define f of 0, for some examples it doesn't help. Not at all. Consider the function from the reals to the reals such that for f of x such that f of x equals 1 over x squared for non-zero x. And let's inelegantly define f of 0 to equal negative 1. And I mean non-elegantly at that. Then f has an absolute and local minimum at 0. Okay. Well, yeah. Okay. Indeed, negative 1 equals f of 0, which is less than 0, which is less than 1 over x squared, which equals f of x for all x in the non-zero reals. However, note that f prime of 0 is undefined because f is not even so much as continuous at x equals 0, and let alone differentiable at x equals 0. Far from it. So here's an example. Here's a weird one, right? This was a really weird example. But yeah, we have a local min at 0, but we're not even so much as continuous there. So that's really weird. And consider f again. If we consider negative 1 over x squared, we have a local max. It's just sort of the reverse, Again, f prime is undefined, because f is not even continuous at 0. It is defined at 0, it's just not continuous there. But anyway, moving along, consider f on a function on the non-zero reals into the reals such that f of x equals negative 1 over x squared. Then f has no extrema at all. Indeed, for any positive m, we can find a non-zero x value such that f of x will be less than negative m. So, we don't have any extrema. Now, as far as having a minimum goes, guys, this right here, this shows this shows hence f has no minimum. All this shows right here is we have no minimum. So for any negative value, it'll equal negative m. Okay. But we can find an x such that f of x will be less than negative m. And because, you can get if x gets close enough to 0, negative 1 over x squared will be even more negative than negative m. So it'll be less than negative m. Like if x is teeny tiny close to, what I'm saying is, if x is teeny tiny negative, like negative 0.000000001, let's say, or negative and teeny, or even tinier than that, but still negative, like negative 0.000 and a whole bunch of zeros after that and 1. Teeny tiny and negative, we can make 0 teeny tiny enough such that, does it really need to be negative? You know what? No, scratch that. Back up. It doesn't even matter. X could be positive. It doesn't need to be negative. We're squaring it, and then we're negating it. So even if x were positive, it wouldn't matter. X could be teeny tiny and negative or positive, and it wouldn't matter. It's going to be negative. It's going to be even teeny tinier in the end because we're squaring it. If you take a number really close to 0 and you square it, you're going to get a number that's even closer to 0. And then if you negate it, you're just going to get a number that's negative and really close to 0. So, and then if you reciprocate it, you're going to get a number that's negative and really, really big. So here f of x is a number that's negative and really, really big. So you can get, as x gets really close to 0, arbitrarily close to 0, f of x goes to negative infinity. Guys, what we're saying here is as x gets close to 0 from any direction, f of x gets arbitrarily close to negative infinity. I think that would have been a better approach. Just to have said, as x gets close to 0, f of x, let's just put that, shall we? Let me just insert that. My explanation here was correct, but a little bit pedagogically hard. Since f of x goes, let me just put, this is a much better explanation. Since f of x goes to negative infinity as x goes to 0, and it doesn't matter which side. Okay. And you know what? Let me just make that my explanation, okay? Let's not get into advanced calculus here, okay? F has no, let's just make that our explanation from the very beginning. So, sorry about that, guys. Let's just do it that way. What I said before was correct but hard, and let's just stick with that. Okay. Now, F gets arbitrarily close. Now, what about max? Max is a little harder to deal with. There is no maximum either of any kind, but it's harder. That may be a harder thing to deal with. Now, F gets arbitrarily close to the x-axis as x goes off to either negative or positive infinity. We have no maximum because F keeps rising more and more slowly as x goes to either infinity. We can't take y equals 0 as a maximum because F never gets there, even though it gets asymptotically close. Okay, and so we have no maximum. All right. Note that f prime of 0 is unhelpful because f of 0 itself does not exist. Yeah, f prime of 0 is undefined, but so is f of 0. So, you know, if f of 0 is rotten, then we can't do anything. We're out of luck. Okay. And then let's get, oh, that shouldn't be there. So let me get rid of that. So that's all for that example. So let's move on. So consider the function f from negative 4 to 2 into r such that f of x equals 5x squared minus 4x plus 1. We know from algebra that no maxima occur and that a local and absolute minimum occurs at x equals negative b over 2a. That's the vertex formula in algebra, which is a is 5, b is negative 4, c is 1. So we have negative 4 over 2a, which is 2 times 5. So that's going to be, the negatives cancel. I get 4 over 10, which is 2/5. And hence, our y-coordinate from algebra, so that's our x-coordinate of our vertex. And then our y-coordinate is going to be f of 2/5. And then we plug 2/5 into this b strut here, and which is what I did right here. And I wind up getting 1/5. So hence, my Cartesian coordinate is going to be 2/5, 1/5. That's my vertex. We could also observe that f prime of x is 10x minus 4, and we set that equal to 0, first derivative. You set the first derivative equal to 0, and you get x equals 2/5. And then you'd plug that back into f again and again, same as before, you'd get 1/5. Note that f is differentiable everywhere, and so f prime is not undefined anywhere. Okay, so you've checked, you've found all your places where the first derivative is either 0 or undefined. It's, there's only one place where it's 0, and there's no place at all where it's undefined. Okay. We found all our critical points. Okay. And consider the function f from negative 4 to 2 into r such that f of x equals this function right here. Now this time we can't resort to algebra. It would be very hard anyway, to say the least. Instead, note that f prime equals 15x squared minus 60, and if we set that equal to 0, we divide everybody by 15, we get x squared minus 4 equals 0. And then we factor by, we use difference of squares factoring, we get that. And then we set each one equal to 0 by the zero factor property. And then we get x equals negative 2. And that should be or, my bad. Either x equals negative 2 or x equals 2. But we only regard x equals negative 2 since 2 is an endpoint. Guys, keep in mind, I'm looking for local. I'm not looking for absolute. 2, it's fine for 2 to be an absolute, but it's not fine for 2 to be a local, okay? F prime of 2 does not exist. There may in another video I may talk about one-sided derivatives, but we're not going to deal with that right now. We're not going there, and we can't do one-sided derivatives for local. One-sided local endpoints will never be local. Extrema, they don't qualify, and endpoints, the overall derivative will never exist at an endpoint either. Don't do it. Okay. Hence, if we have any local minima or maxima at all, then they would occur it would occur at x equals neg 2. But I guess it would be the vocabulary word. But anyway, but 2 is an endpoint in this problem, so it can't be a local min or max. We should still check and see if it's absolute, though. Now, f of 2, if we plug it into f, way back up here, we get negative 79. Now, if we plug neg 2 into f, we get 81, positive. Okay? Now, we got to check neg 4. If we plug in neg 4, we get neg 79. So we have absolute minima at neg 4 and at 2. And we have an absolute and local max at neg 2. Okay?